Okay, so let's begin our section on gases by talking about pressure. So we first maybe should back up and talk about pressure is usually referring to gases. So let's just kind of do a quick review on the three states of matter: solid, liquid, gas. I can do a quick overview. I know you've heard this multiple times in middle school and high school, but I do want you thinking about this from a context of what's going on with the particles themselves. When I say particles in this class, I might mean atoms or I might mean molecules. It's whatever the substance is made of. Okay, so solids, of course, are closely packed particles. So all of the atoms or all of the molecules are very closely packed in such a way that they're almost in a packing pattern, and they are not moving independently, but rather vibrating. So the molecules are moving the whole time, but they're kind of moving together as a pack so that they remain at fixed distances. Liquids are similar. They're fairly close, a little bit further apart than the spacing of the solids, but they can move a little bit independently. So whereas a solid, the two particles may be moving back and forth, but they're staying relative to one another. They're moving together. Liquids now begin to move a little bit differently. But they can't really move too far away from each other. They're still slightly attracted. Gases is where all of a sudden they're significantly further apart and now are totally independent. They don't have anything to do with one another, so they just move around and they collide with each other until they move straight until they hit another particle or until they hit a wall of a container. So how does that arrangement of the particles actually affect the properties that the gas or the liquid or the solid has? We talk about bulk properties. Bulk property means not a property of one atom or 10 atoms, but if I took a sample of trillions of atoms, how does it begin to affect the overall behavior of the group? So again, when we see a solid, that close packed nature and the fact that they can't change the distances between them results in a fixed volume and fixed shape, right? They're going to not be able to change shape because they're all stuck together, and they can't change the amount of space they take up because they're all stuck at the same distance. So if they can't separate or get closer, they can't change volume. And it's very high density. I have a lot of stuff packed very closely together. If I talk about the liquids, then the liquids, because they can move a little bit, now that's going to change their shape. The shape of the solid being fixed is due to the fact that the particles they had to remain next to each other. Since the liquids can move around a little bit, their shape can change, but their volume is not going to change. They're not substantially changing the distance between the particles, so the volume is not going to change. So they're going to have a fixed volume, but a changeable shape. And usually we say the shape of liquid is the shape of the container it's in. And they're still pretty high density, maybe not quite as high density as the solids. Gases, on the other hand, completely independent, so the space between them does and can change, so that the volume is variable, the shape is variable for the same reasons, and very low density. Because there's very few particles packed together in a small area, I have a very low density. Okay, so one of the properties of gases is pressure. It's a property of all items, but we see it manifest itself most uniquely with gases. And pressure in general is the force of an object hits upon a surface. And it's the force pushing against that surface over the area that it's pushing against. So pressure is equal to force per unit area. In gases, the object is the particles, the molecules of gas, and the surface is the walls of the container. So as the particle hits it over a small area, it's hitting it with a certain force over a small area, and that's what the result of the pressure of a gas is from. We have a variety of units. We have millimeters of mercury. By the way, a millimeter of mercury is the same thing as a torr. So if you ever have to do a pressure conversion between torr and millimeters of mercury, it's the exact same number, just change the name of the unit. Atmospheres, newtons per meter squared, which is also called a Pascal, or pounds per square inch. So we have a variety of different ways units that we can measure it, because of course we have different units for force and different units for area, and these are different possibilities. So if I need to convert pressure, and this is a common task, we're going to use a strategy that's called dimensional analysis. We'll talk a little bit more about that strategy when we're going over measurements, but essentially I know that 1 atmosphere is equal to 760 millimeters of mercury, so it's also equal to 760 torr, or it's equal to 101,325 pascals, or 101.325 kilopascals. So I have a variety of different equalities. If I have a measurement, so let's say I'm asked to convert the measurement of 1,570 millimeters of mercury to atmospheres, then this is my starting measurement, and the starting units are millimeters of mercury. So I'm going to make a conversion factor, and the conversion factor is a fraction where the top and the bottom have the same value. However, they're in different units. So 1 atmosphere is the same value as 760 millimeters of mercury. But by putting the millimeters of mercury value on the bottom, the millimeters of mercury units are going to cancel out. And by putting atmospheres on the top, that's what I'll convert my units to. So I multiply this through. So I'm going to multiply 1570 by 1 and then divide by 760. The number I get would be the pressure in atmospheres. Just do be careful that when we say millimeters of mercury or centimeters of water, those are pressure units. When it's added with what it's actually a column of, that's really resulting in the pressure on that column of water or that column of mercury. So it's not distance. You can't use inches to centimeters or anything like that. One way we can measure the pressure is with a manometer. And a manometer is very similar to a barometer. A barometer is a manometer where one end is closed, where both ends are closed. And in this case, it's just a U-tube. It's literally, you could take a plastic tube, put some water in it, hold it up so that it's in a U fashion, and you have a manometer. The idea is that one side is connected to a gas, so this is sealed up. So whatever pressure this is, it's exerting a pressure down on the left column of liquid. And then I have it open to the atmosphere on the other side. So the air in the atmosphere is pushing down on this column of liquid. And the comparison between those, if the pressures are equal, the heights will be equal. But if this pressure is greater, it's going to push down more on the right side, and the open side would be lower. If the gas pressure is greater, it's going to push down more on the left side, and that's going to make the left side lower. So by that, and by the difference in height of these two columns, and knowing what this liquid is, it should be mercury to use a manometer, and we would have to know what is the atmospheric pressure. From that, all that, I can measure pressure. This gives you a better sample of it. So in this case, because the left side is lower, I know that this gas is pressing harder on the left side than the air is pressing on this side. So I know that the gas pressure is higher than the air pressure. And I know it's higher by whatever this height is. So I could measure these. In this case, this is centimeters of water. So this manometer is filled with water, and this is measuring the height difference in centimeters of water, which is a pressure unit. And so I would add it to whatever, I'd have to know what the air pressure is, and I would add the height. Here, they're equal, so no big deal. Whatever the air pressure is, the gas pressure is. In this case, I see that the air pressure is lower. The air pressure is pushing down more on the right side of the column than the gas is pushing on the left side. So that means the gas pressure is less than the air pressure by whatever this height difference is. So I would measure these two heights and subtract them to figure out the difference in height in terms of centimeters of water, which is a pressure unit, and I would subtract that from whatever the air pressure is, which in this case is 1100. So we get the idea of how a manometer could be used and how I could read a manometer to get a measurement. In this case, my measurement would be in centimeters of water, because that is the liquid that is in this particular manometer. So let's talk about temperature. Temperature is really a fairly simple subject. You've had an awful lot of exposure to it before. Let me move that over a little bit. So, let me go back. Let's talk about temperature for a bit. Temperature is a pretty well-known topic. You've had exposure to temperature every day when you watch the news, so you kind of know what temperature is, and yet you don't know what it is. Mostly, I don't want to focus on the basis of temperature. We'll talk about that a little bit more when we talk about kinetic molecular theory, and we did talk a little bit about energy. But I do want to talk about the conversions and the different temperature scales. So we have 3 different scales that are predominantly used. There's even a couple more, but one is Fahrenheit, one is Celsius, and one is Kelvin. So I'm looking at these 3 different scales, and each scale sort of has to have 2 reference points to make it make sense. So 2 different known temperatures that it's based off of. In the Fahrenheit scale, the 0, which isn't really shown on here, but it would be, I'd take 32 down to 0. So the 0 reference point is reference to the freezing point of a solution of brine, the solution of sodium chloride and water and another, I think, ammonium chloride as well. So it's got a variety of salts mixed together. It can get colder than water can. So when you can get that solution to freeze, that's 0 degrees Fahrenheit. And 100 degrees Fahrenheit was based off of the temperature of the human body. Now, we know the normal temperature is 98.6, so it's not quite 100, but this scale was determined many years ago, and so at that point, based off of their accuracy of their measurements, 100 was considered the body temperature. Now, the Celsius scale said, let's reference these things to things that are a little bit more fixed. If you change what you make your brine out of, or you go from different human beings to different human beings, maybe it's a little bit different. But if we take pure water and we freeze it, it will always freeze at a certain temperature. It will always boil at a certain temperature. So Celsius uses the 0 of freezing water and boiling water and the 100 of boiling water to make it scale. Now, once you re-reference this, we need a conversion factor. So for every 100 degrees difference in Celsius, it's 180 degrees difference in Fahrenheit. So that's where we have to rescale things when we're doing our conversions. The final thing is that we have the Kelvin scale. The problem with the Celsius scale is this 0 isn't the coldest you can ever get. The 0 on the Fahrenheit scale is not the coldest you can ever get. You can get colder and colder and colder. Now we go back to what is the idea of temperature. The idea of temperature is related to the movement, the kinetic energy of the particles. So to get 0 temperature, I'd have to freeze the, I won't say freeze. Freeze means something else in chemistry. I'd have to still all the particles so that all the atoms are no longer moving. Now, that's a conceptual limit. We really can't get there. But if I could do that, that would be 0. So the Kelvin scale is based off of understanding what it would need to take to get all the atoms to stop moving, and that's where the 0 is based off. 0 is based off of absolute 0, means there is no temperature, there is no movement of the atoms. And we've successfully gotten down to 4 Kelvin pretty easily. I don't know that we'll ever reach 0, but we can get very close using some different techniques. So the Celsius scale and the Kelvin scale have the same ratio. In other words, for every 100 degrees Celsius difference, it's also 100 degrees difference in Kelvin. So 273 to 373. The only difference is that the Kelvin scale takes the Celsius scale and re-references it to a true 0. For this reason, Kelvin is the preferred unit of temperature for anything that's actually dealing with energy, because it's the one that's really referenced to true 0. So now we have some conversion equations. I've kind of written them out in a variety of ways so that you can understand how we're doing the conversion. So in the case of degrees Celsius, we first need to subtract off that 32 because the water freezes at 32 in Fahrenheit, but at 0 in Celsius. So we have to subtract off the 32, so now they're both at the same 0. And then I'm multiplying it by the difference in the scales. For every 180 degrees of Fahrenheit, it's 100 degrees difference in Celsius. So that's where the original equation comes from. It's often written as degrees Fahrenheit minus 32 over 1.8 or times 5 over 9, right? If I divide these both by 20, this is a 5 over a 9. So 3 different equivalent equations for converting Fahrenheit to Celsius. I can also rearrange them and come up with 3 other different versions from going from Celsius to Fahrenheit. In the case of going from Celsius to Fahrenheit, I want to first rescale it, and then I want to add the 32 to get the difference in temperature between freezing points of water. So in this case, the scaling is 180 degrees Fahrenheit per 100 degrees Celsius, or 9 over 5, or multiplying by 1.8. They're equivalently doing the same thing. So pick one of these to know, or pick 2 if you want to have one for going from Celsius to Fahrenheit and one for going from Fahrenheit to Celsius. Kelvin is the one we're going to use most of the time, this Kelvin-Celsius conversion, and Kelvin is simply the degrees Celsius plus 273.15. If I'm giving you Kelvin and I want Celsius, subtract 273.15. Again, I think we've talked about this sometime along the way, but how many decimal places you use depends on whatever the degrees your measurement is given in. So if you're just told what is 68 degrees Celsius in Kelvin, 68 has no decimal point, so I could just use 273. If I said convert 68.5 degrees Celsius to Kelvin, that has 1 decimal place, so I would use 273.2, what this number would be rounded to the first decimal place. If I say convert 68.39 degrees Celsius to Kelvin, then I'm going to use 273.15. So round this off to match the same number as this, and you'll work out pretty effective.